Welcome to this online course on performance optimization and decomposition methods in Gurobi. This program is brought to you by the Institute of Computer Science at Forth in collaboration with TwinODIS. In this course, we will explore two complementary dimensions of advanced optimization practice. First, we will examine how modern solvers, such as Gurobi, behave in practice. We will study profiling and benchmarking, performance variability, parameter tuning, and the internal logic behind solver decisions. Second, we will study decomposition methods. We will begin with column generation, where we will see how to handle problems with an enormous number of variables by generating them dynamically. Then we will turn to Bender's decomposition, where we will separate strategic binary decisions from operational continuous decisions and structure their interaction through cuts. By the end of the course, you will be able to recognize exploitable structure in optimization models, tune solver performance more systematically, and implement decomposition techniques in a disciplined and technically sound way. Let's proceed with the contents of the course. We begin with tuning opportunities in Gurobi. This includes understanding where computational time is actually spent, how to profile a model correctly, and how to design meaningful benchmarking experiments. Performance improvement always starts with careful measurement. Next, we examine concrete techniques for improving solver performance. We will discuss pre-solve behavior, parameter configuration, and the use of Gurobi's built-in tuning tools. The goal is not to change parameters blindly, but to understand when intervention is justified and when defaults should be trusted. We then introduce decomposition methods, such as column generation and Bender's decomposition. These approaches modify the structure of the formulation itself and can significantly affect computational behavior for large-scale models. Finally, we conclude with a hands-on exercise on a warehouse location problem implemented using Bender's decomposition, allowing us to connect theory, implementation, and observed performance. Before discussing performance tuning, it is useful to step back and examine the full optimization workflow. In practice, optimization begins with a real-world planning system that generates a concrete problem instance. This instance is defined by operational data: demands, capacities, costs, resource limits, network structures. At this stage, the problem is business-oriented. It reflects decisions that must be made under constraints. Next, a configurable model generator translates this data into a mathematical model instance. Here we move from business rules to formal constraints and objective functions. For example, a rule such as each customer must be served becomes a set of assignment constraints indexed over customers. The clarity and structure of this formulation directly influence computational behavior. Once the model instance is constructed, it is passed to the solver, in our case, Gurobi. The solver processes the formulation, applies pre-solve reductions, explores feasible solutions, and searches for optimality. When a solution is found, it is transferred back to the planning system for interpretation and further analysis. The results may lead to revised assumptions, updated data, or modified constraints. This cycle repeats until a satisfactory decision is obtained. Performance optimization, therefore, must be understood within this broader iterative process. It is not just about faster solving, it is about improving the efficiency of the entire modeling pipeline. When we discuss tuning opportunities, it is important to broaden our perspective beyond solver parameters. Performance is determined by the entire optimization environment, not just by the algorithmic engine. First, consider the overall system architecture. In a typical workflow, we have input data processing, model construction, and model solving. These are distinct computational phases. It is common in practice to attribute long runtimes to the solver, while the real bottleneck lies in inefficient data handling or model generation. For example, expensive database queries, repeated data lookups, or building constraints inside deeply nested loops can dominate total runtime before the solver even starts. Second, hardware configuration matters. There's no universally optimal setup. Faster CPUs and additional cores can improve performance, but only if the problem structure allows efficient parallelization. Memory is often the critical resource in large MILP instances. If available RAM is insufficient, the operating system may start swapping memory to disk, which can dramatically degrade performance. In such situations, reducing the number of threads or carefully managing how branch and bound nodes are stored can stabilize execution. Third, data access patterns deserve attention. Long lookup times, poor caching strategies, or repeated recomputation of index sets can slow down model construction significantly. Efficient data structures and disciplined indexing are part of performance engineering. Finally, numerical issues should not be underestimated. Poor scaling, extremely large or small coefficients, and ill-conditioned matrices can affect solver stability and convergence. Reformulating constraints, tightening bounds, or rescaling coefficients often yields more robust performance than aggressive parameter tuning. The central idea is diagnostic thinking. Before adjusting solver parameters, we must identify where time is actually being spent. Effective tuning begins with understanding the full computational pipeline. An important aspect of mixed integer optimization is performance variability. Unlike linear programming, where solution times are often relatively stable, MILP solving can exhibit significant fluctuations, even for the same model instance. One reason for this variability lies in the internal decision processes of the solver. Many algorithmic components involve controlled randomness. Gurobi uses a pseudo-random seed that can influence branching decisions, heuristic solution attempts, and certain internal strategies. Changing this seed does not alter the mathematical model, but it can lead the solver to explore the search space in a different way. Because mixed integer optimization is computationally NP-hard, there is an intrinsic performance variability. Small differences in early decisions may lead to substantially different computational paths. Although some models behave pretty stably, there are pathological models that do not. For them, one run may quickly identify strong feasible solutions and tighten bounds early. Another run with a different seed may explore less promising regions before converging. The result can be noticeable differences in runtime or node counts. From a practical perspective, this has two implications. First, benchmarking should not rely on a single model instance, but it is necessary to use different instances of the same model type. Second, reliable performance evaluation may require multiple runs or controlled experimentation with different random seeds. When a model shows extreme sensitivity, this can be a signal that a structural reformulation may help improve robustness. In general, understanding variability allows us to interpret solver performance more carefully and avoid misleading conclusions from isolated experiments. When analyzing solver performance, the first step is proper profiling. Profiling can be done directly through the Gurobi API. However, for more accurate and isolated measurements, it is often preferable to export the model to an MPS file and run it using the command line interface, specifically Gurobi_CL. Why is this important? Because solving through the API includes model construction time, data handling overhead, and potential Python or system-level delays. By exporting the model and solving it independently, we isolate the solver phase itself. If there's a large difference between API runtime and command line runtime, this is a strong indication that the bottleneck lies in model construction rather than in optimization. Once we focus on the solver phase, the next question is, where exactly is time being spent? The Gurobi log provides detailed information about different algorithmic phases. In particular, we can examine A, time spent in pre-solve, B, time required to solve the initial LP relaxation, C, behavior at node 0 of the branch and bound tree, D, time spent exploring the remaining nodes. Each of these phases can indicate a different structural issue. For example, excessive pre-solve time may suggest redundancy or scale issues. Slow node processing may indicate weak bounds or poor formulation strength. The key is to use the log systematically. The log is not merely informational, it is a diagnostic tool. To facilitate log analysis, Gurobi provides a separate utility called Gurobi log tools, which allows a structured parsing and visualization of solver logs. This can make performance patterns much easier to interpret, especially when running multiple experiments. To sum up, before tuning parameters, we must first identify the true computational bottleneck. Profiling is the foundation of informed performance improvement. After understanding how to profile a single run, we now turn to parameter tuning. Gurobi exposes more than 100 configurable parameters. These parameters control pre-solve behavior, heuristics, cut generation, parallelism, tolerances, and many other internal mechanisms. Importantly, almost 60 of them can directly influence performance. This creates both an opportunity and a challenge. On one hand, there is significant flexibility to adapt the solver to a particular model class. On the other hand, the parameter space is large, interactions are non-trivial, and it is rarely obvious which options should be adjusted first. Manual tuning can quickly become inefficient and unreliable if done without a structure. To address this, Gurobi provides an automated tuning tool called GrubTune. The purpose of GrubTune is to search for parameter configurations that improve performance for a given model or a set of models. The primary objective is typically the fastest time to proven optimality. Secondary criteria may include solution quality measures, such as the optimality gap or objective bound, depending on how the tuning is configured. The tuner can also operate in distributed mode, allowing multiple machines to explore the parameter space in parallel. This is particularly useful for difficult MILP instances where a single-run experimentation is costly. It is important to note that GrubTune is available both through the API and through the command line, although the command line interface provides more advanced features. To use GrubTune effectively, it is important to understand how it operates internally. The tuning process begins with a baseline solve. This baseline uses the parameters you explicitly fixed, together with Gurobi's default values for all remaining parameters. The performance of this baseline, typically measured in runtime and solution quality, becomes the reference point, or score to beat. From there, the tuner does not blindly explore the entire parameter space. Instead, it considers a pre-selected subset of algorithmic parameters that are relevant to the specific model class, such as LP, MIP, or MIQCP. Parameters that are not applicable to the model type are ignored. This already reduces the search space significantly. If desired, the search space can be further customized by providing a JSON file through the TuneParams option in the command line interface. This allows you to restrict tuning to specific parameters or value ranges. An important rule is that any parameter you explicitly set, even if you set it equal to its default value, is treated as fixed. This ensures that certain modeling decisions remain under your control. To reduce the effect of randomness, each candidate parameter configuration can be evaluated across multiple runs using different random seeds. This is controlled through the tune trials parameter. The objective is to avoid overestimating improvements that occur only for a favorable seed. The tuner can also accept multiple model files simultaneously. Finally, by default, the tuner maintains an efficient frontier with respect to the number of parameter changes. It identifies the best configuration with one change, the best with two changes, and so on. This helps balance performance improvement against complexity of configuration. While automated tuning can be powerful, it must be used carefully. First, avoid over-tuning. It is tempting to apply many parameter changes simply because they produce small improvements on a specific instance. However, Gurobi's default settings are carefully engineered and extensively tested. In many cases, less is more. Second, evaluate improvements across multiple test models. A parameter configuration that accelerates one instance may degrade performance on another. When possible, tuning should be performed on a representative collection of instances, and selected settings should demonstrate consistent improvement across that set. Third, automated tuning is not a substitute for sound modeling. If a model is oversized, poorly scaled, or numerically unstable, parameter adjustments will rarely resolve the underlying issue. In such cases, reformulation is often necessary. Another important caution is not to transfer parameter settings blindly from other solvers or even from older Gurobi versions. Parameters are solver-specific, and their effects depend on the internal implementation. Finally, when a new major Gurobi release becomes available, it is good practice to first test the model using default settings. Solver improvements are often embedded directly into the new version, and previously tuned parameters may no longer be necessary. We now move to one of the most important performance components in modern solvers, pre-solving. The purpose of pre-solve is to transform the original model, which we denote by M, into a simpler but equivalent model P. Equivalent here has a precise meaning. If the pre-solved model P is infeasible, then the original model M is infeasible. If P is unbounded, then M is unbounded. If P has an optimal solution, its objective value matches the optimal objective value of M. And finally, any feasible solution of P can be mapped back to a feasible solution of M. Why do we do this? There are three main goals. First, to reduce problem size. Fewer variables and fewer constraints mean smaller linear systems and faster linear algebra during the solution process. Second, to improve numerical behavior. Pre-solve may rescale constraints or tighten coefficients, which improves stability. Third, to preserve the ability to recover meaningful primal and dual solutions after solving. In other words, even though we simplify the model, we must still be able to reconstruct a valid solution to the original formulation. Pre-solve operates at different stages of the solution process. Root pre-solve is typically applied before solving the first LP relaxation. This is where most structural simplifications occur. Node pre-solve is lighter and happens during the branch and bound search. It focuses mainly on tightening local variable bounds based on branching decisions. Now, what kinds of reductions are performed? One major category is variable bound strengthening. Using the existing constraints, we may infer tighter upper or lower bounds on variables. Another is constraint simplification and redundancy removal. If a constraint is implied by others, it can be removed safely. We may also eliminate variables through substitution or aggregate them into other constraints. Coefficient and constant tightening can shrink ranges and reduce numerical instability. Logical and structural simplifications are especially important in MILP. For example, inactive indicator constraints can be removed, or disconnected model components can be separated and solved independently. All these reductions aim at one thing: shrinking and cleaning the model before heavy computation begins. Before proceeding to some concrete pre-solving techniques, there are a few important observations about pre-solve in practice. First, many problem instances are automatically generated. This often introduces modeling artifacts, redundant constraints, weak bounds, or unnecessary variables. Pre-solve is particularly effective in cleaning such artifacts. Second, initial formulations are frequently infeasible or unbounded due to modeling errors. A strong pre-solve phase can detect such trivial inconsistencies quickly, saving substantial computational effort. Third, by inspecting pre-solve behavior in a random optimization solver, and this is not specific to Gurobi, you can draw important conclusions on the quality of a solver. If an optimization solver fails to detect trivial pre-solve cases, such as obvious infeasibility, unboundedness, or redundant constraints, this raises concerns about its reliability. Pre-solving therefore serves as a basic trustworthiness check. A well-designed solver should recognize and resolve simple structural issues immediately. Another important point is that trivial reductions often result from earlier non-trivial reductions. Pre-solve is not just a collection of simple checks. It is an iterative process where one reduction enables another. Understanding this layered structure helps explain why pre-solve can sometimes dramatically shrink a model. To illustrate the pre-solve ideas concretely, we now consider a small example. We impose the constraint 1 less than or equal to 2, x1 plus 2, x2 less than or equal to 3. Variable x1 is binary and x2 is a non-negative integer with an upper bound of 2. Although the example is small, it contains enough structure to demonstrate bound tightening, coefficient tightening, and even variable elimination. In the next slides, we will analyze this model step by step using pre-solve reasoning, not geometric intuition, but algebraic argument. A central concept in linear pre-solve is that of minimal and maximal activity of a constraint. Consider a linear inequality of the form: the sum over I of AI times xi is less than or equal to b. Each variable xii has a lower bound li and an upper bound ui. The minimal activity is the smallest value that the left-hand side can attain, given the current variable bounds. To compute it, we take the lower bound of each variable whose coefficient is positive and the upper bound of each variable whose coefficient is negative. This gives the smallest possible value of the left-hand side under the bounds. Similarly, the maximal activity is the largest possible value of the left-hand side. For positive coefficients, we take upper bounds, and for negative coefficients, we take lower bounds. These two quantities immediately allow structural conclusions. If the maximal activity is less than or equal to b, then the constraint can never be violated. It is redundant and may be removed. If the minimal activity is greater than b, then the constraint cannot be satisfied under the given bounds. The model is infeasible. Let us apply this to our example. 1 is less than or equal to 2, x1 plus 2x2, which is less than or equal to 3. x1 is binary. x2 is an integer between 0 and 2. The minimal activity of 2x1 plus 2x2 occurs at x1 equals 0 and x2 equals 0. This gives 0. The maximal activity occurs at x1 equals 1 and x2 equals 2. This gives 5. So the left-hand side can range between 0 and 5. Since 0 is less than 1, the lower inequality is active. Since 5 is greater than 3, the upper inequality is also restrictive. This simple arithmetic reasoning is the foundation of many pre-solve reductions. Using minimal and maximal activities, we can derive tighter bounds on variables. Suppose we have a constraint where a coefficient of a variable is positive. We can isolate that variable and use the minimal activity of the remaining terms to derive a tighter upper bound. In our example, consider the upper inequality. 2x1 plus 2x2 is less than or equal to 3. If we isolate x squared, we obtain 2x squared is less than or equal to 3 minus 2x1. To obtain the tightest possible upper bound on x squared, we consider the smallest possible contribution of x1, which occurs when x1 equals 0. This yields 2 times 2 is less than or equal to 3. So times 2 is less than or equal to 1.5. Since times 2 is integer, this implies times 2 is less than or equal to 1. We have therefore reduced the domain of x squared from 0, 1, 2 to only 0 or 1. This is a purely algebraic deduction. No branching, no search, or just constraint reasoning. Bound strengthening is powerful because it reduces the size of the search space before the solver begins exploring discrete combinations. We now move to a slightly stronger type of reasoning. Assume that a coefficient is positive, the corresponding variable is binary, and the maximal activity of the constraint minus that coefficient is still less than the right-hand side b. In such a case, the constraint can be reformulated with a tighter coefficient as shown in equation 1. Let us interpret this conceptually. When xi equals 0, the new inequality reduces to a relaxed version that is automatically satisfied whenever the original one is satisfied. When xi equals 1, the term maximal activity minus b becomes active. This term represents the amount by which the worst-case left-hand side would exceed b if all variables were at their upper bounds, so it compensates for the excess and forces the remaining variables to scale down accordingly. In simple terms, the reformulation redistributes slack in the constraint. It strengthens the inequality by explicitly encoding the interaction between xi and the remaining variables. Returning to our example, 2x1 plus 2x2 is less than or equal to 3. After tightening the bound of x2 to at most 1, the maximal activity becomes 4, not 5. Now observe that if x1 equals 1, then 2x1 already consumes 2 units of the right-hand side. That leaves at most 1 unit for 2x2, which is impossible unless x2 equals 0. Careful algebraic manipulation allows us to rewrite the inequality in a tighter form. Eventually, we obtain x1 plus x2 is less than or equal to 1. Applying the same reasoning to the lower inequality gives x1 plus x2 is greater than or equal to 1. Together, these imply x1 plus x2 equals 1. At this point, we can eliminate one variable entirely by substituting x1 equals 1 minus x2. This demonstrates how pre-solve can transform a small mixed integer constraint into an equality that allows variable elimination. The dimensionality of the model decreases before the main search even begins. Gurobi provides parameters that control pre-solve behavior. The parameter called pre-solve controls the overall pre-solve level. A value of -1 lets the solver decide automatically. 0 disables pre-solve. 1 applies conservative reductions. 2 applies more aggressive reductions. Setting pre-solve to 0 can be useful when debugging infeasibility or investigating numerical behavior. Setting it to 2 may help on complex models, but should be validated experimentally. The parameter pre-passes limits the number of passes through the model during pre-solve. If pre-solve consumes too much time with limited benefit, reducing this value may help. For large structured models, increasing it can sometimes improve reductions. The parameter aggregate controls the level of constraint aggregation. In rare cases, aggressive aggregation may introduce numerical side effects. Disabling it can improve stability in sensitive models. The parameter agfill controls how much fill-in is allowed during aggregation. Larger values allow deeper simplifications, but may increase matrix density. Additional pre-solve-related parameters refine specific behaviors. The parameter pre-dep_row controls the elimination of linearly dependent rows. If dependent rows encode modeling a structure, such as symmetry-breaking constraints, you may want to disable this elimination. The parameter pre-dual controls whether pre-solve forms the dual of a continuous model. This can be beneficial when the model has many more constraints than variables. For mixed integer models, it is rarely helpful. The parameter pre-sparsify attempts to improve sparsity by removing small coefficients or rescaling rows. This may improve numerical performance, but in research contexts, you may wish to preserve coefficient patterns exactly. As always, these parameters should be adjusted only when there is a clear diagnostic reason. After discussing pre-solve controls, we now move to more general solver parameters that directly influence MILP performance. Here we focus on 3 particularly important ones: MIP focus, time limit, and threads. Let us start with MIP focus. MIP focus is a high-level strategy parameter. It does not control a single algorithmic detail. Instead, it adjusts several internal behaviors simultaneously in order to emphasize a particular goal. With the default setting, the solver balances between finding good feasible solutions and proving optimality. If MIP focus is set to 1, the solver prioritizes finding feasible solutions quickly. This is useful when obtaining a good incumbent solution early is more important than closing the optimality gap immediately. If it is set to 2, the solver emphasizes proving optimality. This may be appropriate when a high-quality solution is already known, and the main goal is to certify optimality. If it is set to 3, the solver focuses on improving the objective bound, which can be helpful when the bound progresses slowly. So MIP focus is essentially a meta parameter. It steers the search strategy depending on whether your priority is feasibility, proof, or bound improvement. Now consider time limit. Time limit sets an upper bound in seconds on how long the solver is allowed to run. If the limit is reached before optimality is proven, the solver returns the best solution found so far. together with a status indicating that the time limit was exceeded. This parameter is extremely important in production settings. It provides runtime predictability and ensures service level guarantees. If solutions are needed within a fixed window, time limit enforces that constraint. Finally, threads controls the level of parallelism. By default, a value of 0 allows the solver to use as many threads as there are available logical processors. In many cases, this improves performance. However, parallelism is not always beneficial. Some classes of models benefit from fewer threads, especially when memory is limited or when the first high-quality solution is found deep in the search tree. In such cases, allowing a single thread to explore the tree without contention can sometimes be more stable. To better understand the effect of MIP focus, let us examine a concrete, large MIP example with MIP focus set to 1. Recall that a value of 1 instructs the solver to prioritize finding feasible solutions quickly. The emphasis is on improving the incumbent solution early in the search. Looking at the log, we observe that feasible solutions appear relatively early. The incumbent value improves several times in short intervals. The solver is clearly investing effort in heuristics and the strategies that aim to produce good primal solutions. However, notice the behavior of the best bound and the optimality gap. While feasible solutions are improving, the gap may decrease more slowly because less effort is allocated to tightening the bound aggressively. This is a typical pattern when MIP focus equals 1. The search tree may grow and progress toward proof of optimality may be secondary, but good solutions are obtained quickly. From a practical perspective, this setting is often useful in operational environments where decision makers need a high-quality solution within a limited time window, even if optimality is not yet certified. Let us now revisit the same large mixed integer model, this time with MIP focus set to 2. With MIP focus equal to 2, the strategy changes. The emphasis shifts toward proving optimality. The solver invests more effort at the root node. It tightens bounds more aggressively, generates additional cutting planes, and performs deeper root analysis before branching extensively. This stronger root processing increases per node cost. However, the benefit is often a smaller search tree. By tightening the formulation early, the solver can prune more nodes to relieve stronger bounds. If we look at the log, we typically observe A. Slower initial progress in terms of new incumbents. B. More steady improvement in the best bound. C. Higher work per node, reflected in iterations per node. D. Potentially fewer total nodes for difficult instances. There's also a third setting, MIP focus equal to 3. This goes even further in the direction of bound improvement. The solver prioritizes tightening the dual bound over finding or exploiting incumbents. It may spend longer analyzing nodes and generating cuts, especially when the objective bound moves slowly. On easy problems, emphasizing proof of optimality can introduce unnecessary overhead. The additional cutting and root analysis may not significantly reduce the tree because the tree is already small. In such cases, MIP focus equal to 1 or even the default may be more efficient. On harder problems, however, the extra bounding effort of MIP focus equal to 2 or 3 can pay off dramatically. The choice, therefore, is problem dependent. It reflects a trade-off between lightweight exploration with more branching and heavier analytical effort aimed at shrinking the search tree. So far, we have manually adjusted solver parameters such as MIP focus. Gurobi also provides an automated tuning tool called GurobiTune, which systematically searches for improved parameter configurations. Here we focus on the main control parameters that govern the tuning process itself. The first important parameter is time limit. Applied at the model level, this sets a per solve cap. Each candidate parameter configuration is evaluated under the same time budget. This ensures fair comparison, especially when optimality is not reached. In practice, this time limit should reflect realistic production constraints. There is little value in tuning under a time horizon that will never be used operationally. Next, we have tune time limit. This is the overall tuning budget, while time limit controls how long each individual solve may run. Tune time limit controls how long the entire tuning process is allowed to explore alternative configurations. Another key parameter is tune trials. This determines how many times each configuration is tested. Since MILP performance can vary slightly from run to run due to heuristics and parallelism, repeating configurations reduces noise. For serious tuning, using 5 to 10 trials provides more stable comparisons. A single trial is acceptable only for quick exploratory tuning. The parameter tune results determines how many of the best parameter configurations the tuner should keep. Instead of returning only a single configuration, the tuner can store multiple high-performing candidates. This is useful because the configuration that performs best during tuning is not always the most robust across different instances. Retaining several alternatives allows for later validation and comparison. Next, consider tune criterion. This parameter defines how configurations are ranked when optimality is not reached within the time limit. By default, runtime is the primary metric. However, for difficult mixed integer problems where optimality is rarely proven within the allotted time, minimizing the final optimality gap or improving the best bound may be more meaningful evaluation criteria. The chosen criterion should reflect the real operational objective of your application. Another important control is tune params. This allows you to restrict the tuning search space to a selected subset of parameters. Rather than exploring the full parameter space, you can focus on specific controls. This is particularly valuable when prior experimentation suggests that performance sensitivity is concentrated in certain areas. Let us now see how all these tuning controls are used in practice through the Python API. We begin by importing a gurobi PA and loading the model in the standard way. In this example, the model is read from an MPS file. At this point, nothing special has happened. We simply have a model object. The first important step is to define a per solve time limit. We set the time limit parameter to 600 seconds. This ensures that every candidate configuration tested during tuning is evaluated under the same computational budget. Without this cap, comparisons between configurations would not be fair, especially when optimality is not reached. Next, we define the tuning controls themselves. Tune time limit is set to 3,600 seconds. This is the overall time budget for the tuning process. In other words, we allow the tuner 1 hour to explore alternative parameter configurations. Tune trials is set to 3. This means each configuration is evaluated multiple times to reduce run-to-run variability. For more stable benchmarking, higher values may be appropriate. Tune results is set to 5. Instead of keeping only the single best configuration, we retain the top 5 candidates. This allows later validation and comparison. Tune criterion is set to 0, which corresponds to time-based comparison. For harder models, alternative criteria, such as gap-based evaluation, may be more appropriate. After setting these parameters, we call the tune method. At this point, gurobi begins a structured experimentation over parameter combinations. Finally, once tuning completes, we check how many parameter sets were found. If at least 2 configurations are available, we retrieve one using getTuneResult and write it to a parameter file. This file can then be reused in production runs. No, let's move to a new section where we introduce decomposition methods. The basic idea of decomposition is simple. We solve a large optimization problem by breaking it into smaller, more manageable pieces, and solving those pieces either in parallel or sequentially. If a problem is separable or trivially parallelizable, decomposition is straightforward. Each part can be solved independently, and the overall solution is obtained by combining the results. However, the more interesting and practically relevant cases arise when there is coupling between parts of the problem. That is, subsets of variables or constraints interact with each other. In such cases, the subproblems cannot be solved independently. Instead, the overall problem is solved iteratively by repeatedly solving a sequence of smaller problems. that exchange information with one another. In mixed integer linear programs, this structure often appears in what is called a border block diagonal form. There are typically two main scenarios. First, linking variables. We have several independent blocks of constraints, but they are connected through a shared set of variables. These linking variables couple otherwise separable substructures. Second, linking constraints. The variable blocs are mostly independent, but certain global constraints connect them. In both cases, the key idea is to exploit the block structure. We isolate the independent blocks, identify the linking components, and design an algorithm that coordinates the blocks efficiently. Decomposition methods are powerful because they allow us to A. Exploit problem structure, B. Reduce memory requirements, C. Parallelize computations, and D. Solve problems that would otherwise be computationally intractable. In the following slides, we will study two major decomposition techniques, column generation and Bender's decomposition. One of the most important decomposition techniques is column generation. Column generation is designed for solving very large linear programs, especially when the number of variables is so large that we cannot even list them explicitly. Instead of generating all variables at once, we generate them dynamically only when they are useful. The key idea is the following. We start with a restricted master problem containing only a small subset of variables. We solve this reduced model, then we solve a column generating subproblem whose role is to search for a new variable or column that can improve the current solution. This decision is guided by reduced costs. If the subproblem finds a variable with negative reduced cost, that variable is added to the master problem. If no such variable exists, the current solution is optimal for the full problem. So the algorithm alternates between A. Solving the restricted master problem, abbreviated as RMP, B. Solving the column generating subproblem, abbreviated as CGSP, C. Adding an improving column if one exists. This method is particularly useful in problems such as cutting a stock, vehicle routing, and crew scheduling. In fact, column generation forms the foundation of more advanced methods, such as Danzig-Wolf decomposition and branch and price. Let us now formalize the setting. Consider a linear program in a standard form. Minimize C transpose X subject to A, X greater than or equal to B, X greater than or equal to 0, where A is an M by N matrix with linearly independent rows. Now suppose that N is extremely large, so large that we cannot explicitly generate and store all columns of A. In this situation, even computing all reduced costs explicitly becomes impossible. However, if we use the simplex method, we know that at each iteration, we only need to identify one entering variable, that is, one column with negative reduced cost. So the challenge becomes, how can we select the entering variable without explicitly constructing all columns of A and computing all reduced costs? The linear program is solved through a sequence of iterations. Each iteration consists of two steps. A. Solve the restricted master problem. B. Solve the column generating subproblem. Let us now describe the restricted master problem. We solve, minimize the sum over I in I of Ci times X. I subject to the sum over I in I of A. I times X, I is greater than or equal to B, and X is greater than or equal to 0. Here, I is a subset of the columns of matrix A. So instead of using all columns, we only consider a restricted set I. In the first master problem, the set I is selected to include columns corresponding to an initial basic feasible solution, and possibly other important columns suggested by the problem context. We then solve the restricted master problem to optimality. After solving the restricted master problem, we use the dual information to decide whether the current solution is optimal for the full problem. We search for a variable xj with negative reduced costs. This is done by solving the column generating subproblem. Formally, the subproblem identifies the minimum reduced cost over all possible columns. If no column with negative reduced cost exists, then the optimal solution of the restricted master problem is also optimal for the original linear program, and the algorithm terminates. Otherwise, we proceed as follows. First, identify the column J with the most negative reduced cost. Then add this column corresponding to variable xj to the index set I. Finally, resolve the restricted master problem with the expanded column set. This creates an iterative loop. We begin with a starting subset of decision variables. We solve the restricted master problem. We solve the subproblem to check for a negative reduced cost. If no such column exists, we stop. The solution is optimal. If a negative reduced cost column exists, we include the new variable and repeat the process. This continues until no improving column can be found. Let us now discuss some practical variations of the basic column generation method. In the basic version described so far, we add exactly one new column at each iteration. However, if the number of iterations becomes large, the set I of columns in the restricted master problem can grow significantly. This may defeat one of the original purposes of column generation, namely memory conservation, so we consider alternative strategies. A simple, but not necessarily ideal solution is the following. When a new column is generated by the subproblem, it replaces an existing column in I. This keeps the size of I fixed, but may slow convergence. A better solution is to remove columns from I if they have remained non-basic for more than a certain number of iterations. This allows the master problem to remain compact while retaining useful columns. Let us also add some practical remarks. The initial column pool can be constructed intelligently. For example, it may be based on the optimal solution of a similar instance. Also, the ability to efficiently solve the column generating subproblem is crucial. If the subproblem is difficult, the overall approach may not be effective. Finally, the explicit form of the subproblem depends entirely on the original problem structure. In summary, column generation is not just a mechanical procedure. Its success depends heavily on careful modeling of the pricing subproblem and thoughtful management of the column pool. Next, we will see a classical application of column generation, the cutting stock problem. Suppose we have a raw material roll of fixed length L. We are given several item types, each with a specific length and a required demand. The question is, how should we cut the rolls in order to satisfy all demands while minimizing the number of rolls used? Each possible way of cutting a roll defines what we call a cutting pattern. For example, if the roll length is 100 and we have item lengths 50 and 15, we may cut A, 2 pieces of length 50, B, 1 piece of 50 and several pieces of 15, C, only pieces of length 15, and so on. Each pattern corresponds to a column in a linear program. The decision variable associated with a pattern represents how many rolls are cut according to that pattern. The difficulty is that the number of feasible cutting patterns can be extremely large. In fact, it grows combinatorially as the number of item types increases. This is exactly what is shown in this slide. Suppose the roll length is still fixed, for example 100. If we only have 2 item types, say lengths 50 and 15, the number of feasible combinations is relatively limited. But now imagine we introduce a third item type, for example length 25. Suddenly, the number of ways we can combine pieces within a single roll increases dramatically. We can mix 50 and 25, 25 and 15, 50, 25 and 15 together, different multiplicities of each, and so on. Each feasible combination that respects the roll length constraint defines a valid cutting pattern. As more item types are added, the number of feasible integer combinations that satisfy the capacity constraint grows very quickly, and this means that the total number of possible columns in the linear program can be enormous, and so explicitly generating all patterns before solving the model becomes completely impractical. And this is exactly why column generation is essential. Instead of enumerating all patterns, we generate only those patterns that are economically attractive, that is, those with negative reduced costs. Let us now write the mathematical formulation of the cutting stock problem. We define the following parameters L is the fixed length of each raw roll. M is the number of item types. Li is the length of item type I. P is the set of all feasible cutting patterns. AIP is the number of items of type I produced by pattern AP. DI is the demand for item type I. The decision variable is XP, which represents the number of rolls cut according to pattern P. The objective is minimize the sum over all patterns, P of XP. This corresponds to minimizing the total number of rolls used. Subject to A. Non-negativity constraints, XP, greater than or equal to 0 for all patterns P. B. Demand satisfaction constraints. For each item type I, the sum over all patterns, IP, of AIP times XP must be greater than or equal to DI, that is the demand of type I. Additionally, every feasible cutting pattern must satisfy the capacity constraint. The sum over I from 1 to M of Li times AIP must be less than or equal to L for every pattern P. Since the number of feasible cutting patterns can be exponential, we cannot include all variables XP in the model. Instead, we define a restricted master problem. Let P prime be a subset of P, representing the current set of cutting patterns. The restricted master problem is minimize the sum over P in P prime of XP, subject to A, XP greater than or equal to 0 for all P in P prime B. For each item type I, the sum over P in P prime of AIP times XP must be greater than or equal to DI. So the structure of the model remains exactly the same, and the only difference is that we are using only a subset of all possible cutting patterns. We solve this restricted master problem to optimality. If the current subset P prime is sufficient, then the solution will already be optimal for the full problem. Otherwise, we need to identify a new cutting pattern that can improve the solution. This leads us to the column generating subproblem, which determines whether there exists a pattern with negative reduced cost. We now derive the column generating a subproblem for the cutting a stock model. After solving the restricted master problem, we obtain dual prices. Let PII denote the dual variable associated with the demand constraint for item type I. Recall that the objective coefficient of each pattern variable XP is equal to 1, since each pattern represents one roll. The reduced cost of a pattern P is therefore 1 minus the sum over I from 1 to M of PI, I times AIP. So the pricing problem becomes find a pattern that minimizes this reduced cost. Equivalently, since 1 is constant, this is the same as maximize the sum over I from 1 to M of PII times AI subject to the capacity constraint. The sum over I from 1 to M of Li times AI must be less than or equal to L, and AI must be non-negative integers. This is exactly an integer knapsack problem, which is known to be NP hard but well solved in practice. So the column generating a subproblem is a knapsack problem where choice A, the weights are the item lengths Li, B, the capacity is the roll length L, C, the profits are the dual prices PII. If the optimal value of the knapsack problem is less than or equal to 1, then no pattern has a negative reduced cost, and the current master solution is optimal. If the optimal value is strictly greater than 1, then the corresponding vector AI defines a new cutting pattern that improves the solution. We then add this pattern to the master problem and repeat the process. Having seen how column generation decomposes a large linear program to variable generation, we now turn to a second major decomposition paradigm, Bender's decomposition. Bender's decomposition applies to problems where the variables can be divided into two groups. One group contains the complicating variables, which are often integer variables. The second group contains the remaining variables, typically continuous. The idea is to fix the complicating variables and solve the resulting problem in the remaining variables. This defines a subproblem. Instead of solving the full model directly, we construct a master problem defined only in terms of the complicating variables. The subproblem provides information about feasibility and objective value. From this information, we derive constraints, called Bender's cuts, which are added to the master problem for tightening it. So in contrast to column generation, which dynamically adds variables, Bender's decomposition dynamically adds constraints. This process is repeated until no new cuts are violated. So the overall problem has been solved to optimality. In the next slides, we will write a general formulation and derive the structure of the master problem and the subproblem. We consider a mixed integer linear program written in a split form. The objective is to minimize C transpose y plus D transpose x. There are two groups of constraints. The first group is AY greater than or equal to B. These constraints involve only the variables y. The second group is BY plus DX greater than or equal to G. These are the linking constraints. They couple the variables y and x. The variables y are the complicating variables. They are integer and typically represent strategic decisions. The variables x are continuous and satisfy x greater than or equal to 0. The key idea of Bender's decomposition is the following. If we fix y to a specific value, then the remaining problem in x becomes a linear program. The integrality disappears, and the term by becomes just a constant vector. So the model decomposes naturally into two parts. One part decides y. The other part evaluates that decision by solving a linear program in x. Bender's decomposition exploits exactly this structure. We alternate between optimizing over y and solving the corresponding subproblem in x. Now suppose we fix the complicating variables y to a specific value, say y bar. The original objective was C transpose y plus D transpose x. Since y is now fixed, the term C transpose y bar is constant. So the subproblem focuses only on minimizing the remaining term, minimize D transpose x subject to dx greater than or equal to G minus by bar and x greater than or equal to a 0. Notice carefully the structure. The constraint ay greater than or equal to b does not appear in the subproblem. Those constraints involve only y and therefore belong to the master problem. The subproblem consists only of the linking constraints after substituting y bar and the non-negativity of x. So for a given y bar, we solve a linear program in x. Now to derive Bender's cuts, we convert this subproblem to its dual. The behavior of this dual problem determines what type of cut we generate. There are two cases. First case, the subproblem is feasible and bounded, so there exists an optimal dual solution, say UPI bar. Second case, the subproblem is infeasible, which means that the dual problem is unbounded. In this case, there exists an extreme ray, say UR bar, greater than or equal to 0, such that the dual objective grows without bound. We now construct the Bender's master problem. We introduce a new variable z in the master problem, which represents the value q of y bar. So the master problem becomes minimize C transpose y plus z subject to ay greater than or equal to ab and y, satisfying its integrality constraints. However, we must ensure that z correctly represents the subproblem value. This is done by adding Bender's cuts derived from the dual of the subproblem. There are two types of cuts. If the subproblem is feasible and bounded, we add an optimality cut that bounds the objective function from below, gradually tightening the objective of the master problem. If the subproblem is infeasible, we add a feasibility cut so that we exclude y values that make the subproblem infeasible. The stopping condition is the following. If the subproblem is feasible and the optimality cut generated for the current y is not violated, meaning that z already matches the subproblem value with intolerance, then the current solution is optimal and the algorithm terminates. So let's summarize the Bender's method by following the illustrated block diagram. We start on the left by solving the master problem. The master problem decides the values of the complicating variables y and gives us a tentative objective value through the variable z. Once we have this candidate solution, we move to the subproblem. In the subproblem, we fix y to the value just computed and solve the linear program in the continuous variables x. Now we check what happened. First question, is the subproblem infeasible? If the answer is yes, then the current choice of y is not acceptable. So we generate a feasibility cut, add it to the master problem, and go back to solve the master again. If the subproblem is feasible, then we compute its optimal value and look at the dual solution. Second question, does the current master solution already reflect the true subproblem cost? If not, we generate an optimality cut, add it to the master problem, and resolve the master. If yes, meaning the subproblem cost matches the value z in the master, then we have reached consistency between master and subproblem. At that point, the solution is optimal and the algorithm stops. We now move to the hands-on session. We will apply Bender's decomposition to a warehouse location problem. There is an accompanying Jupyter notebook for this exercise that you will use to implement the solution based on Bender's decomposition. Let's begin with the problem statement. A company operates several warehouses that supply customers. Due to increasing demand, the company considers opening new warehouses at candidate locations. Each warehouse has a fixed operating cost and a maximum supply capacity. Each customer has a known demand. There's also a transportation cost from each warehouse to each customer. Our goal is to determine new warehouse locations and supply from each warehouse to each customer, so the total cost, operating plus transportation, is minimized. So we are given the following: the number of candidate warehouses, denoted by N, the number of customers, denoted by M, for each warehouse I, a fixed operating cost Fi, and maximum supply capacity Si, for each pair of warehouse I and customer J, a transportation cost Cij, and for each customer J, a demand Dj. Let's now proceed to the formulation of the problem. First, the parameters. We are given Fi, the fixed operating cost of warehouse I, Si, the maximum supply capacity of warehouse I, Cij, the transportation cost from warehouse I to customer J, Dj, the demand of customer J. Now the decision variables. Xij represents the quantity shipped from warehouse I to customer J. These variables are continuous and must be non-negative. Yi is a binary variable. It is equal to 1 if warehouse EI is open and 0 otherwise. The objective function, which is the total cost, has two components. There's a fixed cost for opening warehouses, and there's a transportation cost for shipping goods from warehouses to customers. The constraints reflect two basic requirements. First, each warehouse has a limited capacity, so the total quantity it ships cannot exceed its capacity, and only open warehouses are allowed to ship. This is the supply constraint. Second, each customer has a demand that must be satisfied, so the total shipments received by each customer must cover that demand. This is the demand constraint. The important structural observation, and the reason we use Bender's decomposition, is that the shipping decisions depend on which warehouses are open. Of course, there are also the domain restrictions. Yi is binary and Xij is greater than or equal to 0. Now we have formulated the full mixed integer model. On this slide, we define the subproblem. Conceptually, the subproblem answers the following question. Suppose we fix the warehouse opening decisions. In other words, assume we already know which warehouses are open. Given those fixed decisions, what is the cheapest way to serve all customers while respecting capacity constraints? So the subproblem is a linear program in the shipment variables only. It contains the transportation cost in the objective, the demand satisfaction constraints, and the capacity constraints, where the capacities now become fixed, right-hand side values, because the binary variables are treated as parameters. From a modeling perspective, this slide performs all algebraic manipulations needed to express the problem in a standard matrix form. All summations are reorganized into compact matrix notation. This step is not about changing the problem, It is about rewriting it in a form that matches the notation used in the slides presenting the theory of Bender's decomposition. Now, we move to the master problem. The master problem contains the strategic decisions, the warehouse opening variables. But instead of explicitly including the shipment variables, it introduces an auxiliary variable that represents the contribution of the subproblem to the total cost. So the master decides which warehouses to open and carries a variable that approximates the optimal transportation cost. The constraints in the master are not the original capacity and demand constraints. Instead, they're the Bender's cuts. These cuts are derived from the dual of the subproblem and progressively restrict the master so that its auxiliary cost variable correctly represents the true subproblem value. Again, this slide performs the algebra needed to express the master in the same matrix notation used in the theoretical development. From here, the algorithmic procedure becomes a direct implementation of the Bender's method we already studied. Now, let's have a look into some practical tips for implementing Bender's decomposition in the accompanying Jupyter notebook. The core implementation idea is that the master problem is solved as a MILP, and during the solve, we dynamically generate cuts by repeatedly solving the subproblem. In Gurobi, the standard way to do this is through a callback. Inside the callback, whenever the solver produces a candidate integer solution for the master variables what do you y, we treat that y as fixed and solve the subproblem. Based on the subproblem outcome, we add the appropriate cutback to the master. To enable this workflow correctly, two parameters are essential. Pre-crush must be set to 1. This ensures that the variables and constraints in the callback correspond to the original model structure, so that cuts are added in a consistent space. Lazy constraints must also be set to 1. This allows us to add Bender's cuts as lazy constraints inside the callback. Now, for feasibility cuts, we need information from an infeasible subproblem. In that case, we rely on Farkas dual information. In Gurobi, this is accessed through the Farkas dual attribute. A practical detail matters here. The extreme ray returned by Gurobi follows a sign convention that is reversed relative to the one typically used in the mathematical derivation. So in the notebook, we flip the sign before forming the feasibility cut. To make this information available, we also set info info equal to 1. Finally, remember that the subproblem constraints depend on the current master solution y. So inside the callback, before solving the subproblem, we update the right-hand side values that reflect the capacities implied by the current open warehouses. Before we conclude, I have included a small set of references for those of you who would like to explore the material in more depth. These references cover both the theoretical foundations and the practical aspects of the topics presented in this course. Let me now briefly summarize what we have covered in this course. We started with performance optimization in Gurobi, discussing profiling, benchmarking, numerical considerations, and parameter tuning. We emphasized that solver performance is not magic. It is shaped by modeling quality, structure, and careful configuration. We then moved to decomposition methods. First, column generation, where we saw how very large linear programs can be handled by generating variables dynamically. Then Bender's decomposition, where we separated strategic binary decisions from operational continuous decisions and structured the interaction between master and subproblem. Finally, we implemented these ideas in a hands-on warehouse location example, bridging theory and practice through a Gurobi implementation. Thank you very much for your attention and engagement throughout this course. I hope the material has been both technically enriching and practically useful.